Now we will see the final, the normal form, and it is Boyce-Codd normal form. So this normal form actually developed by two scientists who developed the relational database theory that we have seen in our, the introductory class of the relational database management system. These two were the scientists in IBM, and they have developed this normal form. So this normal form is given on the name of these two scientists, Boyce and Codd, and that's why it is referred to as BCNF. What is this BCNF, students? Obviously, it's a fourth filter, right? It's not a fourth normal form, it's a fourth filter, because we are starting from 1NF, 2NF, 3NF, and then we are coming to the BCNF. So it's like a fourth filter, and it ensures that uh, this BCNF, if you are satisfying this criteria of BCNF, so it ensures that after you convert the relation into BCNF, it is assumed that, and it is considered as, most of the redundancies or 100% of the redundancies as well as the inconsistencies they are going to remove. So BCNF is the main normal form. If your relation is in BCNF, then it is good to go, and it is good to start with your database design. Then straight away you can create the tables based on this BCNF requirement, and you can start inserting a data in your tables relations, and hopefully there would be no inconsistency, and hopefully there would be no redundancy. What is a definition for this? Obviously, the first thing is the table should already satisfy the criteria of 3NF. So in a serial order, it should satisfy the criteria of the 3NF. Now, this line, it may confuse you, but we'll try to decode this line. If there are any functional dependency where non-super key determinants another attribute, they should be eliminated, right? So what does this line is saying? Every determinant must be a super key. And by the way, what is a determinant? So if you have X is determining Y, so what attribute or what set of attribute will become determinant? Obviously, X will become determinant. So if you have X determine Y and Y is determining Z, or you have W is determining P or any other attribute, so all of these W, X, and Y, in these cases, they are determinants because they are determining the attributes. So what Boyce-Codd normal form says that all of these determinants must be super keys, So if they are super keys, so then our redundancy problem is solved and our inconsistency problem is solved, right? And I'll give you another simplified definition, and this definition you can remember also. It's a very easy definition. So first condition is that relation should be in 3NF. Then the second condition is, if whenever non-trivial functional dependency X determine A holds in a relation R. So there is a relation R in which some attributes are there, and then there is a functional dependency, any functional dependency which holds in this relation, then X must be the super key of R. X must be the super key of R. So if X is a super key of R, then obviously it would be a candidate key also, right? In other words, I said it earlier also, in other words, determinants. What are determinants? That are determining other attributes. So determinants of all the functional dependencies must be super keys. So that's the very simple thing. That's a very simple thing. We'll give you an example, then you will understand more. Suppose that there is a relation R, A, B, C, and D. And set of functional dependencies are A is determining B, and B is determining C, and C is determining D, and D is determining what? A. A simple relation we are just considering. How many attributes are there? 4 attributes are there. So if you try to go for the first normal form, it is already in first normal form. What about the second normal form? So you have to start with the candidate key. What is the candidate key here, students? So if you try to find out A plus, clearly you can see that A is determining B, B is determining C, C is determining D. So you can write it, it is determining A, B, C, and D. Then what about B plus? B is determining C, C is determining D, C is determining E, E is determining F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. So you can write it, it is determining A, B, C, and D. Then what about So B plus also, because D is again determining A, so B plus would be what? B, C, D, and A, right? And then C, if you are trying to find out C plus, so C is determining D, D is determining A, and A is determining B, and B is determining C. So what you will have is C, D, and then A, B. Similarly, you would have D plus, which would be equal to what? D, A, B, and then C. So all the attributes, we have found out that they are the candidate keys. It's like a strongest relation. All the attributes are the candidate key here. So what about the prime attribute, students? Now in this case, you can write it A, B, C, and D. How come they are the prime attributes? Because A is a candidate key, B is a candidate key, C is a candidate key, and D plus is also the candidate key. What about the non-prime attributes? So non-prime attributes, we are not having any kind of non-prime attributes. So you would write null or you would write phi. So non-prime attributes are not there. So if non-prime attributes are not there, so then there is no chance for the partial dependency, because in partial dependency on this side, right hand side, you have what? Non-prime attribute. And in transitive dependency also you have on the right hand side non-prime attribute, but there are no non-prime attributes. So obviously any of the dependency is not either partial and it is not either transitive. So these, all the dependencies or the given relation is in 2NF as well as it is in 3NF, because no partial dependency and no transitive dependency, right, students? Then what about the Boyce-Codd normal form? So if you are checking for the Boyce-Codd normal form, so what I said it, whatever is the determinant, so A is a determinant, B is a determinant, C is a determinant, and D is a determinant, all must be the candidate key. Okay. Super keys, that means it is a candidate key. So we have already found out that all of these are the candidate key. So given relation is in BCNF also, because A, B, C, and D are what? Candidate keys. They are candidate keys. So this is one example of what? Boyce-Codd normal form. So this given relation is in what? Boyce-Codd normal form. Let me give you one simple example, but it is tricky. Yeah, example is simple, but it is tricky. So you have to decompose the given relation with set of functional dependencies into BCNF. That means it is giving a hint that it is not in BCNF. So how can I start? It's already in 1NF, so no need to check for this. Now for 2NF, you have to start. And candidate key, if you try to find out on the left hand side, so A plus is giving straight away, I can see that A, B, and with C is determining B. Or with this first functional dependency only, A, B is determining C, it is giving us C. Then what about C plus? It is giving only C and B. So it is not a candidate key. So only candidate key is what? Only candidate key is what? AB is the candidate key. So what would be the prime attribute, students, in this case? Prime attributes, yes, prime attributes are A and B. Now you have to write A and B. What about the non-prime attributes? So non-prime is what? The remaining attribute, which is what? A C. Non-prime attribute is C, right, students? So here, I think I'm missing one of the thing. And I said it, this is tricky, so even I made a mistake here. And the mistake that I did is I was overconfident and I have not checked for this key, AC. And let me try to see this AC also. So it is giving me A and it is giving me C, and with this C determining B, it is giving me B also, students, right? So this is, a wrong, and that was basically a trick, right? So AC is also giving me the candidate key. So now if you try to find out the prime attributes, what are the prime attributes? It would be A, it would be B, and it would be what? C. And what about the non-prime attribute? In this case, it is phi. So non-prime attributes are phi. So if non-prime attributes are not there, what is the implication for that? The relation is in 2NF, because villain is not there, the problem is not there. And then the relation is also in 3NF, because no non-prime attributes determining non-prime attributes, so no non-prime attributes, so it's already in 2NF and it is already in 3NF. But check for the candidate keys, so you have to check for the BCNF. And here, students, if you check for the BCNF, in case of BCNF, you have to say that AB should be a super key. Right? AB is a super key, no problem. But what about C determine B? So we have already seen that C is not a super key. It is not a super key. Right? So this is causing a problem for BCNF. This is causing a problem for BCNF. So any problem solution is what? A decomposition. So you have A, B, and C, A, B, and C, and this C is causing a problem. So you have to take a closure of C. So it is giving C and it is giving B. So here you would break the relation in R2 and you would write C and B. This is the first decomposition. And then how many are remaining? Only A is remaining, and the common attribute is what? B. Common attribute is what? B. So here R1 is there, which is having A and B, and R2 is there, which is having C and B. So if you apply the functional dependency, students, here, so C determines B is valid, but we have lost this functional dependency. AB is determining C. So there is no functional dependency in this case. No functional dependency. You can write it also, no functional dependency. But still, this decomposition is in BCNF, because all the functional dependencies, just this one, it is having a the left hand side or the determinant is a candidate key. You can see that this is a candidate key. I hope I'm not making a mess here. I'm just trying to solve this problem. Let me write it clearly one more time so that you will understand. So R2 is C and B, students, and C is determining B. So C is a determinant and it is a candidate key. So absolutely it is following a BCNF. For other forms, we have already seen that it is in 2NF and it is in 3NF. Now for R1, what I'm saying is, a student, AB is there, but I cannot write AB is determining C, because C is not there in this case. So we have lost this functional dependency. So this functional dependency is gone. It's vanished. It's Chumantar, right? When it is vanished, so we don't need to check it. But you can say that this decomposition is lossless decomposition, but anyhow could not maintain the functional dependency. So functional dependency preservation is not there, but decomposition is lossless. And finally, this thing is in what? BCNF. Okay, right, student.